Okay, in the next unit, liquids and solids, first we have to talk about intermolecular forces, and then we talked about the phase changes and solids. Liquids and solids are different phases. So when you say a phase is a homogeneous part of a system in contact with other parts of the system, but separated from them by a well-defined boundary. So when you have like two phases, mixture of two phases now in this container, you have liquid and you have solid phase. And when you say phases, you could also talk about the states of the matter, like solid, liquid, or gas. Solid, liquid, or gas phase. Now, in the gas phase, which the substance does not have a definite shape or definite volume, and then when it comes to liquid, is definite volume but not definite shape, and solid is a definite shape and definite volume. Density of solid, because they are more packed, they're higher than density of the liquid or density of gases. And based on their compressibility, we talked about the gases in previous units, that they are more compressible because of the space between them. And the gas molecules, they are in motion, in constant motion, in straight line direction. Liquids, they are flexible in terms of the shape and the shape of the container, but the volume is constant. The reason the volume does not change, because the molecules, they attract each other and they are attached to each other, kind of vibrating over one another. They can move. There's a space between the molecules, slightly enough to make the shape flexible, but the volume is fixed. How do we know there is a space between the molecules of a liquid? Because if you have water as a liquid, you add salt, it dissolves, and you don't see like the rise, a significant rise in the volume, because the salt goes between the molecules. You put sugar, you add sugar, like you can put a cup of sugar into a cup of water, it dissolves. Then you don't have like 2 cups. What happened that you don't have 2 cups? Because the sugar molecule goes in between the liquid, the water molecule. So it has some space for the liquid. For solid, minimum space, and they are rigid, they are in fixed position. The shape is definite and the volume is definite for a solid compound. Okay. What holds the molecules together in liquid or in solid form is called intermolecular forces. They are different from intramolecular forces, because intramolecular forces is the force that holds the atoms of the molecule together. Let's say if I have a polar covalent bond between oxygen and hydrogen, that makes the water molecule. But if I have another molecule of water, okay, another molecule of water, and the two molecules are attracted to each other by hydrogen bonding or by force, kind of like a electrostatic attraction, because these molecules, they are like positive, negative charge, because it's a polar molecule. And specifically, we have like a hydrogen bonding, which we will talk about it also. This bond, the blue color, it shows the intermolecular force is between the molecules. So we have a molecule of water, and there's a force that holds them together. When we talk about intramolecular forces, that is the ionic bond or covalent bond. We talked before about it in previous chapters, and that's the atoms of the molecule. It's held together like the red line. That's the inside the molecule. The intra is more significant than intermolecular force, but intermolecular force, it depends on the nature of the compound. We do have different types of the intermolecular forces. They are known as IMFs, and we will talk about the strength of them as well. Intermolecular forces, it's a great topic in general chemistry 1, because when you get to this part, basically you connect the molecular level of the chemistry to real life. Intermolecular forces for a compound is responsible for its boiling point. So physical property of a compound depends on intermolecular force, or strength of the intermolecular force. Melting point of substance, it depends on intermolecular forces. In a way that if you have stronger intermolecular forces, the boiling point would be higher. Weaker intermolecular force, boiling point would be lower. Same thing for melting point. Heat of vaporization. What is heat of vaporization or molar heat of vaporization? We have definitions in the next slides also, but is the amount of the heat needed to vaporize 1 mole of substance at its boiling point. So the stronger these molecules are held together, basically, the stronger the intermolecular forces, the higher the heat of vaporization is going to be. Heat of fusion is to melt something. A solid that is melted is the same thing. And then heat of sublimation, basically, it's going from solid to gas. But for 1 mole, how much heat is needed to take a substance from solid to gas directly without going to liquid? That is for sublimation. Different type of intermolecular force. We have dipole-dipole forces. That's for polar molecules. So you find this between the molecules of a compound that they are polar and they are molecules. That means it's not ionic compound. For ionic, an A plus and a Cl minus, the electrostatic attraction is between the opposite charges, and this is called ionic interaction. Is the attraction between ions is very strong. For molecular compound, if the molecule is polar, you have the dipole-dipole interaction. The positive side from 1 molecule and negative side from another molecule is attracted, and this force is known as dipole-dipole that holds the molecules together. Okay? The stronger the more polar the bond is, or the compound is, the more polar the compound is, the stronger the dipole-dipole force is going to be. Ion dipole forces, it's going to be a force that holds ion to molecule. Like if you have sodium chloride in water, water molecule is polar. You have the negative positive side for the water molecule, but sodium ion has a positive charge. Positive is attracted to the negative side of the molecule, and the negative ion is attracted to positive side of the molecule. So your molecule must be polar, and then you must have ion. The positive side of the polar molecule is attracted by the negative ion and vice versa. So this is the ion dipole forces. It's more applicable in solution when you have a mixture, because your compound is either ionic or molecular. But if you mix two compounds together, if one is ionic and one is polar, then there is attraction. If this attraction it's there, it helps solubility. Like sodium chloride dissolves in water because water can go from oxygen side and attract the sodium ion because you have a negative side for the oxygen here, pair of unshared electrons, and then hydrogen side of the molecule is positive, and because it's positive on the hydrogen side of the molecule, we talked about this, water molecule is polar, so there would be attraction here as well. And these attractions is going to take the Cl out and then sodium out. They separate the sodium from the chloride, and that basically means that sodium chloride would dissolve in in water because it's a polar solvent. Dispersion forces, those are the forces that basically induced or temporary dipoles that it's going to be between in the molecules that are non-polar. So if the molecule is non-polar and there's no attraction between them, but you could still, let's say you have a molecule of CO2, okay? CO2 is a non-polar molecule. We learned that in previous chapter when we talked about polarity of the molecule, is non-polar. So if this is non-polar and there is no attraction between the CO2 and another CO2 molecule, if there is no attraction, then there should be no liquid or no dry ice. Dry ice is basically solid CO2. But how do we get these to liquid form or solid form? You kind of lower the temperature and you increase the pressure to change the gas to liquid. Now, when you have the CO2 in liquid phase, that means there is attraction between the molecules. So if there is attraction between the molecules, what is that type of attraction? If the molecule is non-polar, then we have like an induced dipole or temporary dipole that is going to be created and then it goes away. So let's say if you have a molecule that is non-polar and you have like electron distribution like this, and then that's like non-polar, okay? Electron distribution like evenly. Now, if you hit this molecule with object or another molecule, the first thing that is going to touch is the electrons. So these electrons are going to push the other electrons away. So as a result, you are going to have then after this pressure, after this force is applied or disturbance is applied, you're going to have a negative charge on this side, but these electrons are going to be pushed away. And if the electrons are pushed away to the other side of the molecule, then this side of the molecule would be negative, this side would be positive. And with the domino effect, because you have more electrons on this side of the molecule adjacent to that, also the electrons would be pushed away to the other side. So then it's going to be negative and this is going to be positive. Now, when you have the positive and negative, then you get that attraction. Since this was originally a non-polar and now is like it's changing to like temporary polar, then it means that you do have a temporary dipole, and that is called dispersion forces. Dispersion forces is for non-polar molecule. Now, if you have two non-polar molecule, like CH4 is a non-polar molecule and C2H6 is non-polar molecule, which one going to have a stronger dispersion forces? Dispersion forces increases by mass. As we increase the mass, we see the increase in mass of the molecule, the dispersion forces also is going to be stronger. So if this one has like this is hypothetical because it's much smaller number. If this is like a 1 degree Celsius boiling point, degrees Celsius, this is going to be like a 2 or 1.5 boiling point. The boiling point is going to increase because the mass has increased, because the intermolecular force has increased. Okay, so from methane to ethane, or the molar mass for methane is 16 gram per mole. 16 gram per mole. This one is a 32 gram per mole. Okay, 16, and this is our 30 gram per mole. 24 plus 6, 30 gram per mole. Then the molar mass is increasing, boiling point is going to increase. These are hypothetical numbers. I don't say that those are the exact numbers. I'm just saying that the pattern is like this, is going to increase. The dispersion forces is going to increase based on the molar mass, and is the most significant or is the only intermolecular forces for nonpolar compound. And other compounds, if you have a compound that is polar, like H2O, we already know that H2O could have dipole-dipole interaction because it's polar. It has also dispersion forces because dispersion forces is for every molecule, but dispersion forces is like a minor force here. The dipole-dipole is more, is major because it's a stronger. And then you have your new one that we haven't talked about is like hydrogen bonding. Hydrogen bonding, water has hydrogen bonding. Hydrogen bonding is very strong compared to dipole-dipole and compared to the dispersion forces. But dispersion forces exist among all molecules, and dipole-dipole is between polar molecules, and hydrogen bonding is going to be very specific. But let's look at the other, continuation of the dispersion forces. So I said, if you have larger mass, the dispersion force is going to increase. As a result, the melting point is going to increase, boiling point is going to increase. You see that all of these molecules are non-polar molecule. If you draw the loose, how do you know is a non-polar? If you have to draw the loose structure and see if all electron domain are occupied similarly or differently. If they are all occupied similarly, they are all non-polar. And if they're all non-polar, the only type of intermolecular force we have is the dispersion forces. And then if we have the dispersion forces increasing as the molar mass increases, then as you go up, down, molar mass is increasing. So molar molecular weight or molar mass is increasing, increases up, down, and the dispersion forces is going to increase. Dispersion forces is going to increase. As a result, as a result of these two, or this is the cause, this is the effect, molar mass is increasing, dispersion forces increasing. As a result, would increase. Okay, so next one. This is just an example. What type of intermolecular forces you have for HBr? So we have to see HBr, is it polar or non-polar? If HBr is a polar molecule, okay, since HBr is a polar molecule, then we know that is a dipole-dipole forces. CH4 is non-polar molecule. How do we know is non-polar molecule? From the VSBR and the polarity of the molecule based on the shape of the molecule, we know that CH4 is non-polar. So since it's non-polar, we have dispersion forces. If you have HBr and CH4, which one has higher boiling point? Definitely would be HBr, because dipole-dipole is stronger than dispersion forces. The stronger the intermolecular force, the higher the boiling point. Now, what about the SO2? SO2, you see, SO2 molecule is not symmetrical. You have sp2 hybrid molecule here. Is a sp2, you have 1 electron domain, 2 electron domain, 3 electron domains. You have 3 electron domains, and then they are not occupied similarly, or you have pair of unshared electron. So this molecule is polar. Because the molecule is polar, the intermolecular force is going to be dipole. So we have dipole-dipole interactions here. So it's going to have higher boiling point, definitely, compared to CH4. And then if you're comparing these two, you have to see which one is more polar and which one has greater mass. If the polarity, if the one is more polar, is going to have higher boiling point. But if they have same polarity, almost same polarity, then you have to see which one is heavier, which one has higher molar mass. Okay. Hydrogen bonding is a third type of intermolecular force, or force, because if you count the ionic, you have hydrogen bonding. It's very specific. So it's only when hydrogen is attached to one of these three, and it has to be directly attached to that. Okay, so let's say if you have like a CH3, CH3, this oxygen is attached to carbon, is not attached to hydrogen, because hydrogen cannot be in between. Okay, hydrogen is basically like this. The molecule has oxygen and hydrogen, but no hydrogen bonding, because there is no OH bond. But if you have a molecule that is a CH3, a CH2OH, so we know that this is a OH, oxygen is attached to hydrogen directly, is going to have hydrogen bonding. If you have NH, is hydrogen bonding, and FH is going to have hydrogen bonding. So if you have NH, FH, or OH bond in a molecule is going to have hydrogen bonding. Hydrogen bonding is strong and is the strongest for molecular compound. If you're not dealing with ionic compound, hydrogen bonding is the strongest intermolecular forces. And since it's the strongest intermolecular forces, is going to increase the boiling point, unusually increased in boiling point. So if you look at these molecules like H2O, in the same group, oxygen, sulfur, selenium, and then tellurium, you have these in the same group in the periodic table. See that the boiling point is increasing based on the mass, but you see like unusual pattern here, like for H2O is much higher than H2S, even though it's lighter, because molar mass for H2O is 2 hydrogen, 1 oxygen, that's 18 gram per mole. But molar mass for H2S, that's 32 plus 2 is a 34 gram per mole. So if both of them are just, polar compound, and they are just based on the molar mass, H2S must have higher. But since H2O has hydrogen bonding, and hydrogen bonding is very strong intermolecular forces, H2O has unusually higher boiling point compared to H2S. But then the trend kind of makes sense, because increasing the mass or molar mass is going to increase the boiling point. HF compared to HCl. HF, hydrogen bonding, HCl, dipole-dipole, because it's a polar molecule. Hydrogen bonding is stronger than and dipole-dipole, so HF has much higher boiling point compared to HCl. Same thing for NH3. NH3 has, now if we say we have hydrogen bonding for water and we have hydrogen bonding for NH3, which hydrogen bonding is stronger? The difference between electronegativity because of the oxygen and nitrogen can answer that question. Oxygen has higher electronegativity, so the hydrogen bonding coming from OH is stronger than the hydrogen bonding coming from NH. So it also depends on the strength of the bond, or difference in electronegativity between the oxygen and the nitrogen, or OH and NH. Oxygen has higher electronegativity. Hydrogen bonding coming from OH is stronger than the hydrogen bonding coming from NH. Intermolecular forces affects the physical property. It affects the boiling point, melting point, like directly. It also affects the other physical property for liquids. This only applies for liquid, the surface tension. The surface tension is the force that you have to overcome, the amount of energy required to stretch or increase the surface of a liquid by the unit area. Basically, if you wanted something to drop in the liquid, it has to overcome the surface tension. The surface tension for liquids increases with increasing intermolecular forces. Okay, and if you have strong intermolecular forces, it's going to result in higher surface tension. Intermolecular forces, it also affects the viscosity, like resistance to flow for liquid. Like if you have concentrated syrup, like a honey, it's not going to flow as much as, as easily as like if you had like an iced tea. It can flow. It's sugar and water. The other one is sugar and water, but the higher the intermolecular forces is going to be, the higher the viscosity is coming from stronger intermolecular forces. So if you have, let's say, molecule that is acetone. Acetone is CH3. CH3CO, CH3, that's acetone. And then you have molecule of CH3, CHOH, CH3. Okay. We have H bonding for this molecule. And we know that is H bonding because we have OH. Here is just a dipole-dipole interaction. Okay, dipole. So which one is stronger? H bonding is stronger. As a result, this is going to have higher surface tension, is going to have higher viscosity, is going to have higher boiling point, is going to have higher melting point. Which one would evaporate faster? Acetone is going to evaporate faster because acetone is the same thing that you find in the nail polish remover. And after is applied, it just dries out on its own. Or if you leave the bottle open, it would evaporate quickly. Alcohol, it will evaporate, but is not going to evaporate as fast as acetone. Has higher boiling point because it has a stronger intermolecular forces. So you need to know the type of intermolecular force to be able to predict the type of intermolecular force if the molecular structure is given or the name of the compound is given, and then relate that to physical property. A stronger intermolecular force is going to be higher boiling point, higher melting point, higher viscosity, higher surface tension. The only thing that is going to be lower is the rate of evaporation. It doesn't evaporate as quickly. So adhesion and cohesion, that's the definition. Just the cohesion is the molecules attract between like molecules. Adhesion is like if the molecules attract between unlike molecules. Like if you have the liquid that likes to climb up the wall, like when you have aqueous solution in a cylinder shape, you see that you have to look for meniscus, and that is the lowest point of the curve. Because of the adhesion forces between water and the glass that you have, because both of them are polar. But cohesion, it would be like attraction between the same molecules. So if you have a liquid like mercury, it doesn't attract by the glass, so it stays like the curved up. This is like stays curved down. So that's some definitions that goes with the adhesion and cohesion forces. Is going to depend on the intermolecular forces. If the liquid and the wall, they have same type of intermolecular forces, it's going to have adhesion. But if they are different, it's not going to have high adhesion. The adhesion is going to be lower. The adhesion force is going to be lower. These are some of the examples for viscosity, measure of fluid resistance to flow. So if you have the higher the intermolecular forces, the higher the viscosity. You see these numbers are increasing, and the reason is increasing is because of the stronger intermolecular forces. So if you have strong intermolecular forces, it's going to have higher viscosity as well. So glycerol has 3 OH bond. If glycerol has 3 OH bond, it's going to have much higher intermolecular forces because you have very high OH bonding there, or high population of OH bonding, and that's why you have like 1.49 is basically higher than everything else in this group. So viscosity, it's affected by intermolecular forces. Hydrogen bonding and water, that affects the property of the water. Like if you have water in the solid phase, the dotted line that you have here is actually hydrogen bonding that becomes rigid. So that makes, if you freeze the water to change the ice, the volume is increasing because of the space that is trapped between the molecules is going to add up to the volume. When you lower the temperature or increase the temperature rather to make it liquid, then the space is going to go away because these are going to be very soft and it kind of overlaps and it fills in the gap. But in the solid phase, these lines are rigid and it traps the space. That's why at 4 degrees Celsius, the density of the ice is the density of the water is the highest at 4 degrees Celsius. So if you lower the temperature, the density at lower temperature, -20 right here, the density is going to be lower. And that makes sense, right? Because when you had the water and the ice cubes would float and it does not sink because ice has lower density than water. Now you know that the reason ice has lower density because the volume of ice increases as it freezes or it changes to ice. The volume increases because of this trapped space between the molecules, and that's because of the hydrogen bonding of the water molecule, which is a great thing to happen because it would make the living for sea, possible. Because when it freezes, it doesn't freeze from the bottom up. The top of the lake, it can freeze, and then there's still life inside underneath because the temperature is the higher temperature water, it goes down, and the fish can survive. Okay. Other definitions we would just want to mention here about the solids. The solids can be like crystalline solids. That means that you do have like a pattern, and organized pattern is very definite shape. For example, you have a unit cell of like a cubic or cubic centered or other names that you would learn later and end of 1046, general chemistry 2. And then you have the amorphous solids that does not possess a well-defined arrangement. So it's more of a disorganized, like glass, like rubber. Those are amorphous. But crystalline solids, they could be like a diamond, like sand, like silicon. Those are crystalline solids. So the different crystals, you could have like the Ionic crystals. Okay, in the Ionic crystals, ions, they are organized in a specific shape. And what you need to, I'm not talking about the shape, memorize the shape, but know that if you have an ionic compound, they're going to have high melting point. They're hard and it's going to have high melting point because they are attracted by the electrostatic attraction by positive and negative charges. So melting point is going to be high. For this chapter, we are more concerned about the pattern in the intermolecular forces, because it's ionic crystals. Intermolecular forces is going to be high because of this strong attraction. Basically, if you are melting, you have to break this attraction. The stronger this attraction is, more heat is needed to break it. So we have the ionic crystals. It's just a type of crystals. Then we have covalent crystals. What's covalent crystals? That could be like a diamond or graphite. Graphite is different from diamond. They're both made of carbon, but they're slightly different from one another. The bond that it holds every carbon to another carbon in diamond, it's all like covalent bonding, and it's very strong. But for graphite, it goes with the layers. The first layer is held by the covalent bonding, and then the two layers are not. There's a space between them, and they are not held by the covalent bonding. It's just the van der Waals force that holds it. So every time you slide your pencil over paper, you remove like one layer of this carbon, and you leave the mark on the paper, because of this bond between the layers is not very strong. The melting point for the covalent crystals is very high as well. Okay, so it's not ionic, but it's like very specific. Like you have diamond, you have like quartz, and like silicon dioxide. They have very high, like sand. They have very high melting point. Molecular crystals, they could be like, these are all other solids that they are not ionic, they are not the covalent ones or covalent crystals, and these compounds, they have low melting point. Okay, they could have very low melting point. So this is like a dry ice, has very low melting point, because it depends on intermolecular forces. So we have the molecular crystals. These are molecular compounds that they are being compressed, or they are heavy, and they stay in solid phase. So they are molecular crystals. Metallic crystals, these are metals. So it's just metals. And when we talk about the metals, they could have high melting point, they could have like low melting point. Like mercury is liquid at room temperature, but then you have iron that melts at the like 1500, and then you have like aluminum that melts at 700 degrees Celsius. So it depends on the metal. It could have from low to high melting point. They're good conductors of heat and electricity by metallic bond. Metallic bond means that you have plus charges fixed, and then the electrons are moving around. So plus charges are embedded in the sea of electrons. This table shows a summary of different crystals: ionic, covalent, molecular, or metallic, with some examples. Okay, some examples. So you have quartz or SiO2 and diamond. These are very specific, so you don't have to look for like other examples. So at least you know that diamond and quartz, they have very high boiling point. But molecular compounds, that if it's like argon in solid phase, or CO2 in solid phase, or sucrose in solid phase, these are molecular, and they have relatively low melting point. But the higher the molar mass, the higher the London dispersion, and the higher the melting point is going to be. So you have some examples to look for. The amorphous solid or non-crystalline, it has unorganized shape. You see some of the openings here, or even the number of the atoms in each side or in each part, it's different. So it's very unorganized. That's non-crystalline or without crystallizing. So it's a glass example of it. But if you have the crystalline quartz, the silicon dioxide, it's very organized. They're all exact same shape and the same form and same size, and it's very organized. So that's the definite shape that, the well-defined shape that you have for each unit. Okay, we talked about intermolecular forces. We talked about different type of solids. Now, how the intermolecular forces are going to affect the phase changes. What is phases? We talked about phases. That was the first slide. Like if you have a solid phase, liquid phase, or gas phase, what happens? And how do you change the phases? If you change the temperature, you change the phases. For solid going to gas or to liquid, you have to increase the temperature. If you want to go from gas to liquid, you have to lower the temperature. If you want to go gas to solid, you have to lower the temperature even more. So solid, they are most order. And if you want to go to liquid, you have to break some of the bonds. So you have to spend energy. If it's liquid going to gas, you have to break all the bonds between the molecules, between each unit. And then you have to evaporate it, change it to gas, and molecules in the gas phase, they are moving constantly. So if they want to stay in the gas phase, they have to have a lot of kinetic energy to be able to move constantly. So phase change requires changing energy. If the temperature changes and the phase does not change, but still your molecules is going to move faster, basically at a higher temperature, kinetic energy of the molecule is going to increase. And at one point, if it reaches to a point that they can fly, like from liquid to gas, then it would change to gas. If they cannot fly or they cannot leave the liquid phase, they are still moving faster in a hot liquid compared to cold liquid. So the higher the temperature, the higher the kinetic energy is going to be, because kinetic energy is a stored energy, is coming from the heat you apply. We have another definition based on dynamic equilibrium, and dynamic equilibrium, that means that phase change is reversible. Like if you're going from solid to liquid or liquid to gas, liquid to gas is called evaporation. So this is a liquid to gas, and then condensation is gas to liquid. So if changing gas to liquid and liquid to gas happens at the same time with the same rate, we know that we have dynamic equilibrium. So is the equilibrium between the phase changes is a dynamic equilibrium. Okay, rate of evaporation and rate of the condensation, if it's the same, then we know that equilibrium has been established. What is vapor pressure? We talked about the vapor pressure for gas. We talked about manometer in the last unit, or unit 5 or 6, that manometer that is used to measure the pressure of it has to be closed container, otherwise is the atmospheric pressure, is not the vapor pressure. So in a closed container, you can measure the pressure applied. As you increase the temperature, the vapor pressure is going to increase. At one point, when the vapor pressure equals atmospheric pressure, the liquid would change to gas, or boiling can take place. So basically, boiling point is a temperature, which in that temperature, vapor pressure of the liquid equals atmospheric pressure. So they can move up quick. Heat of vaporization. What is heat of vaporization? Is the heat that needs to vaporize a liquid. But when you say specifically a molar heat of vaporization, when you talk about molar heat of vaporization, that is for 1 mole. 1 mole of a substance. And the symbol is going to be delta H vape. That is molar heat of vaporization. Then is the energy required to vaporize on 1 mole of that liquid, okay, at its boiling point. So vapor pressure, it can change by the temperature. It can change by the R value. So pressure can change with this, you know. So we can see that as you increase the temperature, the vapor pressure is going to increase. You increase the temperature, vapor pressure is going to increase. And if we have the atmospheric pressure at 1, at this point where the vapor pressure line is going to cross the 1 atm line, boiling will take place. So 34.6 is going to be the boiling point of diethyl ether at 1 atm. And the mercury is going to boil at 357 degrees Celsius at 1 atm. Now, if you increase the pressure, what's going to happen if you increase the atmospheric pressure to 2 atm is not going to boil until over 400. The mercury is not going to boil. It's going to boil at the higher temperature. So if you increase the temperature, vapor pressure is going to increase. But when the vapor pressure equals atmospheric pressure, boiling will take place. Boiling could happen at any temperature, any pressure. But when you talk about normal boiling point, we do have definition for normal boiling point. Normal boiling point is the boiling point at 1 atm. So molar heat of vaporization, again, is the energy required to vaporize 1 mole of the liquid. Boiling point is the temperature at which equilibrium, its reached vapor pressure of the liquid equals to atmospheric pressure or external pressure. But when you talk about normal boiling point, the external pressure is a fixed number, is 1 atm. So boiling point can be measured at different atm or at different external pressure, but is not going to be standard. The standard one is when they keep the pressure constant, and then they only write those numbers in the books based on the boiling point or normal boiling point. So the numbers that is recorded in the books as a boiling point, that's actually normal boiling point, or it happens at a fixed atmospheric pressure. Water would boil at 100 degrees Celsius under 1 atm external pressure. External pressure, if it's 1 atm, methane, CH4, would boil at -164. Why water is boiling at higher temperature compared to methane? Because water has higher, stronger intermolecular forces. Molar mass for water is 18, for methane is 16. The molar mass is not much of a difference, but intermolecular forces for water is hydrogen bonding, and for methane is dispersion. So you see the difference of over 200 degrees Celsius in difference in boiling point. That's because of the difference in the intermolecular forces that we have. What is critical temperature, critical pressure? That would be easier to show it to you show it to you in here in a phase diagram. Critical pressure or critical temperature, it would be somewhere here, and then critical temperature is the temperature that you cannot change if the liquid changes or the sample, the substance reaches that temperature, you cannot change it back to liquid. Is like the super value. It's a critical temperature, and that temperature then when it is going to change to gas, and you cannot change it back to liquid. The temperature above which the gas cannot be liquefied, no matter how great the applied pressure is. So critical temperature is the pressure at the critical temperature, basically. That's easier to see, but it's the minimum or pressure that must be applied to change to liquid. So when the critical temperature is a very high temperature, then requires a very high pressure to bring it down. So when you look at in the graph that I showed you, like it was a point of the temperature line, then it's going to be, let's say, up here if it's the critical temperature, and then you have the pressure. So anything below, right below, you can look at the pressure that can change the sample to liquid. But anything higher, if it doesn't matter how much pressure you apply, is not going to change to liquid. Phase changes, melting and freezing, evaporation, condensation. So melting, solid changes to liquid. Freezing, liquid changes to solid. Evaporation, so vaporization, liquid changes to gas. And condensation, gas changes to liquid. Sublimation, liquid, solid would change to gas without going to liquid. And if it goes back, it's called deposition. Deposition, that would be gas going back to solid without going to liquid. So here we're just talking about melting point of a solid and freezing point of the liquid. It's going to be same temperature, right? Solid and liquid, they're going to be in the dynamic equilibrium. In the dynamic equilibrium, that's when you have your solid and liquid in the same container. The temperature is going to stay constant until all the solid has changed to liquid. So we have the melting point, and then this is the delta H fusion. Melting point is the temperature. Delta H fusion is the amount of energy. Is the same thing as the melting. Okay? Delta H of fusion is the amount of energy needed to melt 1 mole of substance. So this is the amount of energy that you have to apply to change solid to liquid, but at its melting point. There is no change in temperature. It's just changing phase. We do have a next diagram is called a heating curve that shows the phase changes. Let's say if we're talking about water, okay? Let's say we're talking about water. What would be this line here? Melting point is going to be 0 degrees Celsius. That's at 1 atm, okay? Water at 1 atm. So 0 degree. And then this is going to be 100 degree because it's 1 atm. Boiling point is going to be at 100. So what do we have here? Let's say here it could be like a minus 25 or minus 30 degree. It's just a number, but it has to be less than 0 to make sense. Because if it reaches to 0, it would start melting. So what is happening in this segment of the graph? You are applying heat. So heat is applied here. So you're applying heat. The time means that the time that you apply heat. Okay. So as you apply heat to solid, the temperature is going to increase. So in this case, it's just warming solid until it reaches melting point. When it does reach melting point, it's going to start melting. And until it goes from point A to point B, that means all the solid has been melted. The temperature is going to stay constant. So solid and liquid in equilibrium in this area, there is no change in temperature. So if there is no change in temperature, you have to only use the heat of fusion or heat of vaporization, but you cannot use the value for Q, or you cannot calculate heat based on change in temperature. At point B, So at point A, we have solid at, so A, solid at melting point. B, we have liquid at melting point. Everything has been melted, okay? Melting point. What happens between B and C? You are still applying heat. The liquid is going to increase temperature. So change in temperature. So temperature, anywhere here, you're going to have liquid, but as you get closer, the liquid is going to have higher temperature, okay? Because this is the temperature line. It's as you get closer, the temperature is going to increase. When it reaches to point C, the liquid starts boiling. So C is the liquid at boiling point. C, liquid at boiling point. And D is going to be gas at boiling point. But after everything has changed to gas, the more heat you apply is going to increase the temperature of the gas. So you have to see where is, how much heat is needed to go from solid to liquid, and then how much heat. So you have to pay attention also to these phase changes, that when the phase changes is happening, the temperature is not changed, but heat is needed. You see, it doesn't happen right away. You apply more heat in order to change from liquid to gas. Everything will change to gas. Okay, so we have our phase changes for like molar heat of sublimation. What's going to be is going to be the amount of heat needed from going from solid to gas directly, and depositions gas to solid directly. But the total amount of the sublimation is going to be equal to fusion plus vaporization. So it's kind of a, you add the two together in terms of the values. So let's see an example. Look at an example of how much energy is required to vaporize 20 grams of ethanol at its boiling point, and its heat of vaporization is 40.5 kilojoule per mole. So if we have this value in kilojoule per mole and we have a gram here, it's kind of is a hint for us that it has to be the same unit, right? It has to be same unit. So this is expressed based on the kilojoule per mole of ethanol. So we have to change this to number of moles first. To change the number of moles, we need the molar mass for ethanol, and that is 2 times 12 for carbon, plus 5 times 1 for hydrogen, or 6 times 1, because we have another hydrogen here, plus 1 times 16 for oxygen, and that adds up to 46 gram per mole. So we have 46 gram per mole. That's the molar mass for the ethanol. We start with the 20 gram times 1 mole over 46 gram. This would change the moles of the gram of ethanol to moles of ethanol. And then you can say for 1 mole, for every mole of ethanol, we need 40.5 kilojoules. You can do into 2 steps or just use all in in one step. Okay, so this number, whatever you find, is in kilojoules, is going to be whatever you find here in kilojoules is going to be the amount of the heat needed to go from to evaporate 20 grams. This happens at boiling point. So if it happens at boiling point, what it means is that is not going to involve any changes, any of the temperature change. So at the boiling point, you have 20 grams of ethanol, you want to vaporize it, you need that much of the heat per mole, so you change to moles first. So I'm going to use a calculator, 20 divided by 46, and that number times 40.5, that equals 17, so 17.6 kilojoules of heat needed to vaporize 20 grams of ethanol, because for 1 mole we need 40.5. And next example, okay, that is like a phase change. So we have 18 grams of water, a liquid at 65 degree to 115 degree gas. So for this, first thing I'm going to do, I'm going to look at the phase diagram. What does the phase diagram show me? The phase diagram was like this, okay? So you should be able to build your phase diagram. Okay, so this one, we have here solid, here is liquid, and here's gas. Now, because this is water, I know that this is a 0 degree and this one is a 100 degrees Celsius. It gives me 65 degrees Celsius, so I know that I don't have to deal with the solid or changing my solid to liquid. It starts somewhere here, okay? It starts somewhere here, so I'm going to only use this segment of the graph. So I start at 65 degrees Celsius, that's what I have. And then it's going to change to 115. So here is a 100 degree, and this is a 100 degree. 115 is going to be like here. So I need to calculate each segment. So I need some heat to change the temperature from 65 to 100 degree. I need some heat. If I call this A, then I need some heat to change from 100 degree liquid to 100 degree gas. Then I need to change from 100 degree gas to 115 degree gas. So that is a segment C. And for each one, I have to decide, am I using Q or I'm using a delta H. When there is a change in temperature, you would use the formula of Q equals mass times specific heat times change in temperature, when you have change in temperature. If there is no change in temperature, you are going to use the heat as N times delta H. So Q is going to be N times delta H. So delta H that we have here is going to be vaporization, because we are not doing the fusion. We are only doing the vaporization. So these are the two choices. For A, what should I use for A? I'm talking about this A, that's A. For A, I see that for A, there is a change in temperature going from 65 to 100. So I have to use this Q. There is change in temperature. No temperature change. No delta T, okay? Delta T, in this case, delta T is 0. In this case, delta T is greater than 0. So delta T equals 0. We use this formula. If delta T is greater than 0, we use that. So for A, delta T is greater than 0, and delta T is actually what? Delta T in this case delta T for A equals 100 minus 65, which is 35 degree. Okay, so I'm going to use the first formula with the delta T greater than 0. Mass is given to me as 18 gram times a specific heat for water is given, for the liquid part is given, is a 4.18 joule per gram per degree Celsius. And then delta T is calculated as 35. And I'm going to find this value and record that number is 18 times 4.18 times 35. And that is 2,633 joules, or 2.633 kilojoules. So we decide later which one we are going to use, the joule or kilojoules, because when you're adding diff A, B, and C, they must be either in joules or they must be in kilojoules. Now, for B, what I need to do for B, is there a change in temperature? For B, there is no change in temperature. It's a flat line for the temperature line. There's no change in temperature. So I have to use the N times delta H vaporization. In this area, when vaporization takes place, I have to use delta H vaporization. If we had this area, any changes from solid to gas, we have to use the delta H of fusion. So for this one, for B, I'm going to need the N. What is the value for N? I start with the 18 grams and multiply that by 1 mole over 18 grams. And this gives me 1, okay? This gives me 1 mole. Times delta H of vaporization is given here, 40.7 delta H of vaporization, and that's in kilojoule per mole. If I multiply this number, I get 40.7 kilojoule, because I already know that is 1 mole, so this is going to be kilojoule. So I have the kilojoule and I have kilojoule. I have to now calculate C. What's happening in C? There is a change in temperature. So if there is a change in temperature, should I use 1 or 2? I said if there is change in temperature is greater than 0, I have to use 1. So I'm going to use the formula 1, and Q equals mass. I have 18 gram times a specific heat, but a specific heat for gas is different from the liquid. So I have to look at the table, 2.01, and that is joule per gram per degree Celsius, times, what is delta T? Delta T in this case is 115 minus 100, because it's going from 100 degree to 115, and that would be 15 degree Celsius. You see, units are going to cancel. The units, degree Celsius would cancel with this, gram would cancel with this one. Whatever number you find is going to be in joules. So 18 times 2.01 times 15. This is 542.7 joules, and that equals 0.542 kilojoules. Okay, kilojoules. Now, I have the value for A plus B plus C. I have to add all 3 of them, as the Q equals A plus B plus C. And that is, you just add the 3 together. That would be 2.633 plus 40.7 plus 0.53. 0.542, and the answer is going to be, this is going to be 43.875, and unit is going to be kilojoule. This much of heat is needed to go from 65-degree liquid to the 115-degree gas for 20 grams of water. Okay, next, dealing with the phase diagram. What is a phase diagram? Phase diagram is lines or the graph that is going to summarizes the condition at which substance exists as solid, liquid, or gas, and these conditions are temperature and basically pressure. Because if you increase the temperature, solid would go to liquid and liquid would go to gas. And at different pressure, that change in temperature is going to be different. So you have to consider both factors, pressure and the temperature. So this line right here, you have solid, liquid, and gas. You see, at lower pressure, you need less change in temperature or lower temperature to go from solid to liquid. If the pressure is less than 0.001, there is no liquid there. It would be gas all the time. Okay, so it's important to know about these lines. That point here is called TP or triple point. Okay, critical point is up here, CP, and this is a TP. This area, you have the solid, liquid, and you have the gas. This line here, if I call this like a B, and I call this one A, the AB line is the equilibrium between solid and liquid. So melting is taking place at this line. Okay, melting is taking place at this line. So if I have a C here, AC, this line, boiling takes place. Boiling take place. There is one point that is called normal boiling point. So this is the N boiling point, normal boiling point. But any of these points is boiling point. So boiling point can happen at any temperature, but normal boiling point is the temperature that happens, boiling happens at under 1 atm. And we have the triple point. That means that it connects solid, liquid, and gas. This line here, if I call this one D, AD line, this is known as sublimation line. So you have the equilibrium between gas and solid directly. At a very low pressure, sublimation could take place. At very low pressure, solid can evaporate, go to gas phase directly. For carbon dioxide, the phase diagram is very similar. Just as a review, this is just as a review, you have the triple point here, you have critical point there, you have your sublimation line here, sublimation, you have melting, okay, melting. When I say melting, you already know that melting and freezing takes at the same time, solid, liquid, and then this part is boiling. Okay, boiling takes place under this condition. This is just a condition at this pressure and this temperature you have. Now, if you have a point here, okay, a point here or a point right here, I'm going to call this one. What's the temperature? Temperature is minus 78. But the pressure is 5.2. At 5.2 pressure and 78 temperature or minus 78 temperature, CO2 is going to be solid. But if you increase the temperature to minus 50, minus 50 is going to be here, right? Minus 50 at 5.2 is going to change to liquid, or at the let's say 57, 67 is going to change to gas. So you are moving this from solid to liquid to gas as you increase the temperature. So if more lines and the numbers are given here, you should be able to say any of these conditions, like at this temperature, this pressure, Okay, this pressure and this temperature, your sample of CO2 is going to be in liquid phase. So you just have to find the corresponding. If the question is this, you will get the values. Okay. You might have noticed that the melting line for carbon dioxide and for water is slightly different. Okay, the melting line for water is the slope, or this line is going toward the lower pressure, and then for CO2 it goes at the higher. It goes toward the higher basically higher temperatures. Okay, so the line, the angle here, you see that is basically the slope is positive. For water, I'm just going back and forth so you could see it. The angle, the slope is like a negative slope. What's the difference here? It's saying that for water at very high pressure, the sample is going to exist as a liquid, not solid, if you increase the pressure. We saw before that if you, in the water molecule or inside the water molecule, there are spaces. So if you put like lots of pressure here, lots of pressure is going to squeeze the molecule and it would change to liquid. That's kind of the explanation. That the difference for water, the water line, the melting line for water in the phase diagram is negative slope, and then for carbon dioxide it was like positive slope for CO2, and this is for H2O. The difference is coming from this space here. If you put high pressure, it takes lower temperature, or at lower temperature it can go to liquid because of this spacing that is here. Okay, now that I'm going up here, I have a couple more examples for you. I want to talk about those examples. Which of the following substances should have the highest boiling point? Going back to intermolecular forces, because the phase diagram was the last slide for this unit. We have to look at the different compound. This is like a non-polar. Okay. Non-polar. And then you have magnesium oxide ionic. If you have ionic, then is it ionic? And if it's ionic, and we said that intermolecular force for ionic is going to be the most, or the strongest one, and that's going to give the MgO as the highest boiling point. So highest boiling meaning that strongest intermolecular forces. The intermolecular forces is going to increase, or would be highest for ionic. Then is H bonding. Then is dipole. Then is the dispersion. So we find here ionic, we find here dipole, and these three are dispersion. Ionic is the strongest intermolecular force. It would result in highest boiling point, highest melting point, highest viscosity, and highest. Okay. Another example we have here, it says, choose the pair of substances that are likely to form homogeneous mixture. What does it mean? It means that intermolecular forces must be similar. What type of intermolecular force you have for ethanol is H bonding, right? H bonding. For hydrocarbon, anything that has only carbon and hydrogen is non-polar. And if it's non-polar, it's going to be dispersion. Okay? So you have dispersion forces only here. they're not going to make homogeneous mixture because the intermolecular forces are completely different. One is H bonding and one is dispersion. For this one, NH3, because it has an NH, is going to be H bonding. And then CH3OH is H bonding. H bonding is going to give homogeneous mixture. So this is the answer to the question. Largest dispersion forces. So example of that, I had example already. Let's say you have CH4, you have CCl4, and you have CO2. Okay, they're all nonpolar, and we want to know which one has the largest dispersion forces. So what you need to do, find the molar mass. So this is going to be 44 gram per mole. That's coming from 12 plus 16 times 2. 44 gram per mole. That is 12 plus 4 is going to be 16 gram per mole. And this one is a 4 times 31. That's like 142 and then 154. 154 gram per mole. 154 gram per mole is the highest mass. They're all nonpolar, and it's going to be highest London dispersion. Okay. That's concludes the presentation for the unit of liquids and solids with sample problems.